Welcome to the third segment on the topic of ratio and proportion. In this segment, we will take a look at further applications to chemistry, such as limiting reactants. And just to recap what we've been doing so far, in part one, we looked at basics of ratio and proportions. And we also looked at some applications to chemistry, such as mole-to-mole conversions in a chemical equation. In part two, we looked at further examples on mole-to-mole conversions. And here we are looking at the last application from chemistry on the topic of ratio and proportion, and mainly limiting reactants will be our focus. So here we have a chemical equation, and this one actually is not balanced. So I thought I should also give you a preview about how to balance equations. But you don't have to worry about it. If you don't get that part of the video, please don't worry about it. But it's quite simple, at least the example that we have right now. So here we have iron oxide plus carbon that yields iron plus carbon monoxide. So starting with the most complicated one on the left side, we have Fe2. So here on the right hand side, I have only one Fe. Therefore, I'm going to put a coefficient of 2 in front of the Fe on the right hand side to balance them. So there were 2 iron atoms here, so now I have 2 iron atoms on the other side. Okay, here you have O3, so there's 3 oxygen atoms. So the only term has oxygen here is this one. I'm going to put a 3 in front of that one to make that one 3 oxygen. But when you do that, the carbon is also multiplied by 3. So to balance that out, I'm going to put a 3 over here. So now we have a balanced equation. Again, you don't have to worry about that initial step. It's just a preview to what you may be seeing in your chem classes. Now let's focus on part B. Fill in the following table. Use the given quantity in moles to determine the missing quantities. And something we pointed out in the last few segments is the equation gives you, the balance equation gives you basically the code that must be satisfied in terms of ratios of moles. So if you use 1 mole of this quantity, you must use 3 moles of this quantity, and it's going to yield 2 moles of this and 3 moles of that. So that gives you the blueprint of what kinds of proportions you should be using. So if you have now 6 moles of carbon given, let's look at our equation here. So you have 3 moles of carbon, you will yield 1 mole of iron oxide. But we have 6. So there we see a very clear pattern, right? It was exactly doubled. So we can use the same pattern here, double that one. Again, if there's nothing in front, you can assume there's a hidden 1 there. So now we're doubling it, so that'll be 2.0 moles of iron oxide will be needed. And how many moles of iron will be produced on the right-hand side? So if the carbon, the 3 moles of carbon, now we have 6, has been doubled, then the 2 moles of iron will also be doubled. So if we start with 6 moles of carbon, we're going to end up with 4 moles of iron. And similarly, carbon monoxide will also be doubled. So you'll end up with 6 moles of carbon monoxide. And in this case, let me leave the answer in terms of significant figures, in terms of 2 significant figures. So 4.0 and 6.0. So that's because we were given 2 significant figures in the given problem. Okay. In the next part of this question, we have a different situation than the ones we've been working on before. Here, let's read the question. So if 3.0 moles of iron oxide reacts with 4.0 moles of carbon, which one will be used up completely? Also indicate how much of the excess reactant will not be used up. So far in the examples we've dealt with, we were given just one of the reactants amount, and the other ones were filling the blanks. But this time they gave us the amounts for 2 of the reactants. And we need to see if they come in the correct proportions, because if not, there's going to be some leftover from one of the quantities, and the other one will be used up completely. But then we need to figure out which one will be used up and which one will have excess remaining, assuming that they're not given in the correct proportions. So let's see. So here we had our equation, the same chemical reaction equation I just copied over here. So we're looking at the correspondence between iron oxide and carbon, and in the given equation, coefficients were 1 to 3 ratio. So 1 mole of this will react with 3 moles of that. What we have right now is 3 to 4 ratio. So let me write that down. That's the given information. We have 3 moles of this quantity, the first one, and 4 moles of the second one. If we look at the ratio that's given to us, this is the correct ratio. It has to be 1 to 3. So carbon has to be 3 times as much as iron oxide. We certainly don't have that relationship here, right? If it was 3 times as much, you would need to have a 9 there, but we don't, right? So what that tells us is we don't have the 9, so carbon will be used up first. Basically, we're not going to be able to use this entire amount of Fe2O3 because we don't have 9 moles of carbon. So what we're going to do then is now that we realize, okay, so carbon is our limiting reactant. That's the one that's going to be used up first. So carbon is the limiting reactant. So let's begin with how much carbon we have in answering the question, in finding out how much excess will be formed. So 4 moles of carbon properly reacts with how much iron oxide. So let's figure that out. So begin with 4 and find out how much iron oxide that will be going into reaction with. So here I set that up already. So the unknown is Fe2O3, the quantity of that. We have 4 moles of carbon. And here's our conversion factor that's given to us in the 1 to 3 ratio. 1 mole of iron oxide to 3 moles of carbon. And the way we write them down is so that we can cancel the carbons. We can be left with what we're looking for. And there we have it. Cancel the same units from the top and the bottom. So we have basically 4 over 3 moles of iron oxide. In other words, the two significant figures, 1.3 moles of iron oxide. So that means there's going to be excess, right? Because we were given 3 moles of that compound, and we're only using 1.3. So the amount of the excess is 3 minus 1.3, which will be 1.7 moles of that molecule will be excess. It will not be used up in this reaction. So that's the answer to this blank here. Okay, moving on to the next part of the question. Based on the given information we just obtained, and assuming that the reaction goes to full completion, indicate how many moles of iron and carbon monoxide will be formed. So here I again copy the same equation from the top over here. The ratios were 1 to 3 to 2 to 3. Now we know from the previous example, previous part of this question, that we can only use 4 moles of carbon. Even though we were given 3 moles of iron oxide, we couldn't use all of that, right? So we now know we can only have 1.3 of this quantity that will react with 4 moles of carbon. Now the question is, determine how much iron will be produced and determine how much carbon monoxide will be produced. Now of those two questions, carbon monoxide is the easier one, right? Because the ratio is 3 carbon to 3 carbon monoxide. So that answer is already we know. If you use 4 of this, that will be 4 as well. 4 moles of carbon monoxide. But let's figure out the iron. The ratio is 3 to 2, and we're given 4 moles of carbon. So let's figure out how much iron that we produce through this equation, through this chemical reaction. So, and I've already set that up over here. We want to know how many moles of iron we are given 4 moles of carbon, and to be more exact, that was 4.0, and I'll put a squeeze in a 0 in there as well. So we have 4.0 moles of carbon. And the conversion factor is 3 moles of carbon to 2 moles of iron. And I write the carbon at the bottom because when I cancel the carbons, right? So let's go ahead and do that. Cancel. And the remaining will be 8.0 moles of iron. And the answer will be 8.0 divided by 3 moles of iron. And to the appropriate significant figures, we can leave the answer as 2.7 moles of iron. Let's take a look at our next example. Okay, once again, we have an equation that has already been balanced this time. Part A is asking us how many moles of iron oxide are produced when 7.0 moles of oxygen are used up in this chemical reaction. So how many moles of iron oxide are produced? So we've done many of these questions before, so I'm going to give you guys a moment to do this, and I'll show the answer on the screen for you. And here's the solution. On the left-hand side, you see the solution with the dimension analysis approach, and on the right, the solution with the ratio proportion or equation approach. Either way we solve it, we end up with 4.7 moles of iron oxide. Okay, let's take a look at the second part. So for this question, we're given 6 moles of oxygen that is reacting with 10 moles of iron. And the question is, which reactant will be used up first? So let's look at the proportions that were given to us in the equation. So 3 moles of oxygen will react with 4 moles of iron. For the given information, we have 6 moles of oxygen and 8 moles, rather 10 moles of iron. So if we form a ratio, the correct ratio is 4 to 3. What we have is 10 to 6. That's the Fe to O2 ratio on both sides. Now, for this situation, we can clearly see this is exactly twice as that. As a matter of fact, if we get the common denominators, so we can clearly see that for 6 moles of oxygen, you really need 8 moles of iron. So these 10 moles of iron is in excess. We're actually going to have 2 moles of iron in excess there. So again, here there was a clear pattern. From 3 to 6 it was doubled. So you can see from 4 to, it should be 8 moles of iron, but we had 10. So we can then see that, so this one should be 8 to 6, Fe to O2 ratio, but we had 10 to 6, Fe to O2 ratio. So we know that this one is in excess because this was given in the equation. This is the correct ratio. These are the substances given in our problem, and they were not in the correct ratio. And we can see this will be in excess, and this will be used up first. So that means oxygen is your limiting reactant for this question. And because you only need 8 moles of iron to react with 6 moles of oxygen, you're going to have 2 moles of iron remaining. So that will be the reactant left over, and how much the answer will be 2 moles. So oxygen will be used up first, therefore it's the limiting reactant. 8 moles of iron will be used, and 2 moles of iron will be remaining. Okay, at the moment, do not worry about this part of the question. I'd like to introduce to you the last part of the question on the next page. So we have the same equation, but this time we have 7 moles of oxygen reacting with 10 moles of iron. And the question is, what will happen in that situation if you combine them? Will there be an excess? Which one will be used up first? How much of the excess reactant will be remaining? Now I picked this example because in the last one we went from 3 to 6. There was a very clear pattern there, so we could do the doubling effect here. But this is not an exact whole number multiple of 3, right? Therefore, it's a little bit trickier. But we can solve it without a problem. So here's what I did. I put the correct ratio on the left-hand side based on the equation 4Fe to 3O2, and that's what I've entered over here. This is the correct ratio given in the equation. This is the materials that we have in our hand. 10 moles of iron to 7 moles of oxygen. The question is, are they going to be, is this the correct ratio? Is everything going to be used up, or is something going to be left over? And the best way I know to compare fractions is to get common denominators. Now, on the last question, we just multiplied this one by 2 over 2 to get 6 on both sides, on both denominators. This time, there is no number you could just multiply one fraction by. So what you really need is least common denominators. And to get that, this top and bottom will need to be multiplied by 7. And this top and bottom by 3. That way, it's as if you're multiplying this side by 1, this side by 1. You're not changing the value, but you're rewriting your fraction. In a way, it's going to be easier to compare. So now we have 28 over 21 on this side, 30 over 21 on that side. Now, this is the correct proportion you should have, because this came from the coefficients in our equation. And this is what we were given. So if you have 21 moles of O2, you should have 28 moles of iron. But here we have 30, 21 to 30. So you can see that this is going to be in excess. That means iron will be the one that is in excess. And oxygen is the one that will be used up first. Now, you cannot, though, conclude how much excess, because we changed the given information. You were not really given 21 ounces or 21 moles of oxygen, so you cannot now conclude as 2 moles in excess, because this is not what we really have. From this information, all we're obtaining is that which one is in excess and which one is used first. And our answer is oxygen is used first. And whichever one you have more limited amount, in this case oxygen, so use that one to answer the question. That we know our limiting reactant is oxygen, we're going to begin with that given amount of oxygen to determine how much iron can go into reaction with that given limited amount of oxygen. So we had 7.0 moles of O2. Again, we know O2 will be used up first. We're trying to figure out how much iron will go actually into reaction with the limited amount, 7.0 moles of O2. Here's our conversion factor. 4 moles of iron to 3 moles of oxygen. That's given from our equation. And if you simplify this, multiply the tops, you have 7 times 4, divide by 3, you will have 9.3 moles of iron. And I forgot to mention that you should cancel the units moles of oxygen from both the top and the bottom. So we're left with 28 over 3, or rounded to the 2 significant figures, 9.3 moles of iron. Okay, so if that's how much is used with 7 moles of oxygen, and because we were given 10 moles of iron, then what's the remaining amount? So that would be a simple subtraction problem. Just go 10.0 minus 9.3, and then we will have 0.7 moles of iron that is unused. So that concludes our session on ratio and proportion. So we started with a very simple example with oranges all the way back in the first segment, and look how far you have come. Congratulations, and I hope that having seen this material will help you in your chemistry classes.